So next up, we have Naresh talking about Outlook Service. So Outlook Service is the one that actually backs Office 365 and Hotmail. And one of the things that Naresh is going to talk about is the choices they made in terms of how to scale. Do you couple compute and storage? Do you actually couple hot and cold data? And some of the unconventional path they actually took to get where they got to now. Thank you, Naresh.
Thanks. Can you hear me? Great. I'm Naresh Sundaram. I'm an engineer in the Outlook service. I'll be talking, as G2 said, about a couple of interesting design choices that we made in the Outlook service. Share some perspectives, what we have learned. That might be interesting for this audience. Maybe it'll move. All right. A quick introduction. And before I actually get into that, a couple of high-level observations. One is, I think this talk is a bit of an outlier, I think, from all the rest of the talks, or most of the talks here, in that most of the talks here are about algorithms and data structures and that level. This is intentionally done at a slightly higher level about some higher-level design choices that we have made and what we have learned from that. And I'm just picking two to keep the talk very short and very focused, which is the next point, which is it's a very small slide deck and a short talk. You can go back to the coffee break even sooner, and I'm happy to take questions outside too. All right, so with that, so what is Outlook Service? Outlook Service is the service, you may be familiar with Outlook Client to read email and calendar on your Mac or your Windows. The service that is behind it in the cloud is Outlook Service. It's the unification of what used to be two separate services run in Microsoft. The commercial service, the Hotmail, or it was recently, or some years back, branded as Outlook.com. That's the consumer-facing mail and calendar service. And then we had the Exchange online service. That's the service we sell to businesses, both on-premises, and we now run it in the cloud. So the Outlook service is the name we are using where those two services are being combined. And that's a work in progress. And in this deck, I'm talking as though it has already happened, but it's happening as we speak, right? And we are merging those two services. And the Outlook service you can think of as one of the key pillars of the Office 365 suite of services that Microsoft offers for our primarily targeting businesses to give them productivity services. The familiar Office clients, as well as the services that back up those clients in the cloud. It's a healthy business for Microsoft. I think it's doing very well. And the Outlook service is a key part. Messaging and calendaring is such a key part of the overall time spent by most information workers that you can think of it as kind of the base on which the rest of the Office 365 service is being built or sold. Or that could just be my bias since I work on that. A few quick numbers about the scale. And actually, I did have a line before that I took out, I think. We started this service 2011. We launched Outlook Office 365 2011. So it's about 4 years. And maybe we were in beta a year or so before that, so 5 years. And the growth has been pretty impressive. We are very proud of it. We have more than 2 million businesses that are paying customers that love the service, and they have trusted their data and their productivity with our hands. And it's growing very well. We have over 500 million accounts across our consumer and our business services, with about 50 million, I would say, engaged users, like daily engaged users there. About 70 or more billion transactions. I'm loosely calling messaging transactions a day. Think of that as sending a mail or getting a mail or reading something. Those types of high-level transactions we do about so much. We have over 100,000 servers in our service today, and it's grown pretty fast. And spread across like over 50 data centers worldwide in about 40 countries. And that's kind of a key point, which is when we sell to organizations, data sovereignty comes up as a pretty important issue. Companies in Europe have strict residency requirements for their data and their compute to be in Europe. And in fact, some countries go even further, like Australia wants it to be in Australia, not even in the rest of APAC. And Germany wants the data to be in Germany. So this model is really geared to how can we go broad, very broad, with relatively small footprint, because we may only have say, 200,000 users in a given country, and we should still be profitable in that footprint, right? It's not necessarily always millions, right? We have about more than 300 petabytes of logical data in the service, and over exabyte physical, if you include replication, the copies that we keep. And the service is running at more than 4 nines availability. And again, being a commercial service, this is actually a money-backed guarantee. In our contract with the customers, we give them the guarantee, I believe, of 395, which if we lose, we have to pay them back money, so we take it pretty seriously. And in this talk, again, super short, I'll just go to talk about 2 design choices that we made that in some sense goes counter to many other services that you're familiar with, that you're building probably has adopted. I'll share that, and I'll share some perspectives as to what's worked, what's not. The first one is the service composition, is the way I'm calling it. And the picture shows how a conventional cloud service might be built. I think most of what we heard about in the talks are built along that model, where you have several independent services that follow good SOA principles, good contracts, good versioning, run independently, deployed independently, along those lines. And they all have their own partitioning model and their own sharding model. Whether it is how do they partition data or how do they partition compute, each service makes its own choice and say, hey, it's good for me. One might be sharding based off of how many transactions it needs to service a shard. Another one might say, I care about the volume of the data, and I'll shard along those directions. Another one might say, time is my primary bit. I'm going to partition on time. And it's very free, very democratic, right? And you build services that way. And there are many services, some for data, some for cache, like memcached, some for, say, NoSQL system for that blob store for a blob data, and on and on. And that's how it's done. And typically, and again, this is not always, they are expected to be co-located in the same data center because these services talk a lot with one another. They have a lot of interactions, and often expectations that these calls are order millisecond or few milliseconds is the expectation. So it's typically built that way, right? In contrast, the Outlook service has taken a very different approach. Where we flipped the problem entirely on its head and say that data sharding is the most fundamental thing, and it's not an option that every service gets to make. We have kind of said, we would pick the sharding model up front in terms of what makes sense to our service. And our service being the Outlook service, users and groups are at the core of what the service is all about. Right? So we assert that the data sharding, and each shard corresponds to either a user or a group. And those are the shards. And we say that that's the partitioning model. And on a given server, we will say, you're going to place this many user shards and this many group shards spread using any load balancing techniques that you want. And once that placement choice is made, all the component services, they don't have any more degrees of freedom. They just come and run there. So you can see that service 1, service 2, service 3, one of them being a cache, one of them being a compute, one of them being a store. It doesn't matter. Whatever you are running in the server with the shard, right? So we flip the problem in that sense, right? And this, the service contract between the services follow your normal SOA in terms of the principles that you need. Failure resiliency, versioning, all of that is still applied. But we take away the freedom of the instance, like for each instance of the service to decide where it gets to run. It just runs where the data is, right? So this kind of shows how the system works from the outside, given this model. So you can think of requests coming in from our clients or from other second-party, third-party services. And we have a request routing, a software-based network routing layer, where it takes a look at the request that's coming in. This is maybe some user coming to read his mail, or another user coming in to accept a meeting request in his calendar, whatever the request is. The routing plane is smart to examine the request very superficially, just enough to know what is the data shard that is most naturally affinitized to service this particular request. Because the requests have pretty good affinity with respect to the data shards. And the reason is we didn't pick the shards arbitrarily. We actually picked the shards that map very well to our application domain, which is users and groups. So as a result, we can take any request that comes in, we can say this request is for this user, this request is for that group. And even if the request, for example, deals with multiple users or multiple groups, you can pick one as the primary and route the request to that server. So the routing layer knows that at any given time, any given shard is active on a specific server. And there is, of course, high availability. There are 4 copies. They can fail, all of that. So it takes care of that, and the request lands on the server where the shard is hosting that. All the compute services and the rest of the services now run right there on that server. They may need to call out to other shards to pull data. So if it's a distributed transaction where you're making a call to look up the calendar availability of 5 people, I have to go fan out to 5 other shards to pull the calendar details of 5 other people to return back to the client. And that is what is shown in this internal lines. And those calls also gets made through the same routing plane. There isn't another system to go make that call. And when the request is fully executed, call is returned to the client. So that's a very simple high-level overview of how this service works in this model. Few advantages that we have with this model compared to the conventional model. The first one is a really, really, really simple horizontal scaling model where, like in 5 years, we have grown from nothing to 100,000 servers and over an exabyte of storage. And we think that one of the ways, and I'll like to talk about that, I think this architecture has helped us make it really simple. We stamp out servers, we provision some shards to run on it, and that's it. It just grows. We don't have to worry about, is this service scaling, is that service scaling, this has a bottleneck, that has a bottleneck. We don't have to worry about any of that. It just works. We just keep scaling horizontally, right? The next one is very important, the super low latency cross-service calls. So within a data center, in the conventional model, you still have a network, even though it's a local network, to make the calls across services. So we have kind of taken this philosophy of take compute close to the data to the limit, which is, think of how you'll run your typical Hadoop-like systems, where you take your batch processing code and you ship it to where the data is. We have now done that for all our transactions, where the transaction runs right next to the data. So it's super low latency, and calling multiple service components involved to interact with the data is pretty low cost. Like, we are talking microseconds in terms of that latency. So that lets us enable very rich and deep scenarios that require a lot of compute data interaction. We can just afford it very easily. It's right there. And related to that is very efficient cache utilization. The moment you take compute away from the data and you scale out compute differently, you get into this classic cache coherency problems and cache dilution problems that you solve by then placing another cache tier that single instances it. We don't need it. Cache is right there with the shard. The cache also distributes naturally with the data shard. So it's very, very efficient. The failure mode is simple. The server is either healthy or it's not healthy. When it's not healthy, we turn it off. All the shards go somewhere. They spread. And the individual services follow in lockstep. So you don't have failure modes where you're somewhat working, where service 1 is working, service 2 is not, service 3. No. Either it works or it doesn't. It's very easy to debug, explain, and to explain to customers as well as to ourselves. The small failure domains, and I think that's key, because in the conventional architecture where you have lots of services built this way inside a data center, this becomes a failure domain. And I can share one example that occurred to us in 2012, June 2012. And that's a good point to say that we started off in this model. So we didn't build the model from the get-go. We were also in this model. And in 2012, when we were in this model, a pretty bad outage happened to us that shook us up. At that time, we were about 1 year into the service, having launched in 2011. It's a big outage. So what happened was, in one of our data centers, and even then, we had many data centers, right? We had like 8 data centers, I think, at that point around the world. In one data center in San Antonio, a network upgrade caused a Byzantine failure on some set of data nodes. The failure was not black and white. It was gray. And those are always, as you all know, they're the worst, right? It's not a clear failure. So calls that used to normally take a couple milliseconds were now taking a second or 2, and often more, and then timeout. And it was random. So depending upon which compute server hits which data server, it would have this erratic behavior, right? So this caused the compute services to start having problems. They were building request queues. It also started affecting how the compute services talk to one another, in that the queues were building in the paths where we don't typically expect queues, where it wasn't hardened enough to handle the queues. So slowly, the system was grinding to a halt. And at some point, a threshold was reached where it was just thrashing, where the entire system was just thrashing. Retry, failure, Byzantine failure, cross-service dependencies. And we were still new at that point, relatively new, to running that service. And it was hard to actually get out of it. And it lasted more than 2 hours, that outage. And before we could figure out what happened, and it got rolled back, right? So that was like a lesson learned. And we still have most other services in Microsoft that are built in this model. And periodically, we hear about outages along those dimensions from them, right? The thing is, these are rare outages. They may happen once in 2 years. But when they happen, oh my God, the risk is super high. So I kind of think of it as insurance policy. Yeah, you're not going to get into the accident, but oh boy, when it happens, you better be insured, right? And so the decision that we make to go in this model kind of splits it around, which is we take lots and lots of failures, but they're all small. A server fails, and it fails a lot, right? And 0.01% of the users at that point are impacted, and they are affected for 10 minutes. And we have that daily. It happens all the time, and we just take it. But we avoid big failures in this model. Right? And the last point is coordinating complex changes across services becomes very simple in this model, where especially the specific case where you need to make a data format change and need to make some compute change in coordination with that. When you split them out, rolling those upgrades and operationalizing it is non-trivial. I think you guys all know that. The model where you take the data and compute right next to one another means that you can rev them pretty easily together. And that's been another big advantage as we have been revving the service. All right, so that's that. I'll just quickly jump to my second design point, which is co-location of data itself, not about data and compute. Okay? So this is the conventional way by which we often deal with data in many of the services. You compartmentalize data into cold data, warm data, hot data, cache data, metadata, blob data, text data. And you'll dish it up this way. You'll have a memcache-like system to keep track of your cache. You'll have a metadata system like Cassandra, Postgres, RocksDB, the 2 others that you heard, to run your metadata system. We have a text index, maybe Lucene, Solar, homegrown, to manage your text indexing. You'll have some files and blobs in some relatively cold storage, and even colder storage that I think a couple of more talks are coming behind this that'll talk about how they store cold data. And that's how you build the service. And again, it follows the classic service-oriented architecture, where each guy just develops his part of the puzzle and things come together, right? And it works for the most part, which is why it's so popular, right? So we've taken a different approach to this, and we have again flipped the problem around on its head, that too, and says, no. The data shards are the most fundamental thing, which is the users and groups. So for a given shard, we say we will co-locate all the data, whether it is metadata, text index, blob data, reference data, I don't care, cache data. For a given user or for a given group, all the data is kept together on the same server. And with respect to the hard drives, we actually mix the cold and hot data and metadata in the same hard drive spindles. So the model is something along these lines. So there is a cache tier where we use RAM cache and an SSD cache to cache the hottest data. And then we have the metadata and the text index in hard drive, a lot of which also will be in the cache tier. And then we have this bottom of the pyramid, which is the hard drive with lots of cold data of various levels of coldness, mails that you may have gotten a week, mails that you may have gotten 5 years ago, they're all sitting there, right? So that's the model. And the key is the last point, which is that they all cohabitate the same set of hard drive spindles. And that's pretty key. So what's the advantage of this approach versus the conventional approach of splitting data differently? The first thing is, again, it's a simpler engineering system. We have one way to scale and one way to run the service, and it just runs. And we couldn't have, with our expertise in service scaling, reached this scale in 4 years had we gone some other route. So it's really simple to run it. We think it's very easy, and we know that in practice as we develop features, there are many features that naturally cut across these artificial lines we may draw about what is cold, what is hot, or what is metadata and what is blob data. Like, for example, a simple example. So I got an email, and it's got a huge amount of text in the body, maybe worth a meg of text, let's say. Well, you think of it as that's kind of blob. I want to kind of store it as a file somewhere. But you get the second email that's, hey, where are you? And that's the whole text, right? That's metadata. But from the data model point of view, they're both body. And there isn't really any fine line that says the how are you text becomes a different data model than this big, long email that had a couple of pictures embedded inside of it. And we don't sweat. We just say, yep, It's all together, and it's just body, big, small, I don't care, put it in, right? And we can develop features that cut across. That's a very simple example. There's more interesting examples that cuts across these natural lines often that just falls into place. We don't have to worry about, does it go here, does it go there? No, it's just there. Keeping the warm and the cold data on the, actually before that, total COGS is lower. All up, if you look at the Outlook service cost, compute cost, SSD cost, RAM cost, disk cost, we believe this model gives us efficiency in that combining all of them and not having separate fleets of capacity for each one gets the total cost of running the service lower. We have keeping the warm and the cold data is a win-win in the following sense. As you all know, hard drives, the capacity is growing quadratically. It's areal density. The IOPS, random IOPS is flat. It's not growing at all. And sequential IOPS is growing linearly with linear density, right? Now, by putting them together, the warm data benefits and uses what little IOPS there is. And the rest is compensated by cache and SSD. Cold data comes in and just occupies the space. So it's like a marriage made in heaven, right? We don't waste either one. We use up all the resources as much as we can. Then the key point is the next one. The incremental cost of cold data is really, really low. Think of it this way. We think that the bulk of the cost of cold data systems is in keeping the disk spinning and powering them, and the compute fabric that goes around it, the enclosure, so to speak, dominates the cost, not the byte cost on disk or on tape, or the media cost. So in this case, that's free. You already got a server with its compute, with the spinning disk being paid for by the warm data, not by the cold data. So we think of the cold data cost in that model, it comes to less than a cent a gig a year is the cost of cold data, right? Which gets me to the next point. The absolute number is now so small that from a business model point of view, cost doesn't matter, value matters. Which is, if I can make your productivity, say, if I can improve your productivity by a minute a day, that translates to $1 a day in many cases. And we say that, and the reason why that's possible is that because the cold data is right there, we can analyze it all the time very easily. We have lots of natural free cycles in our service, whether it's night, where there's a lot of free time, or whether opportunistically, during even except for the peak 3 hours, we have lots of cycles available in all the rest of the system because we are provisioned for peak, because we have to handle peak capacity, where we cannot turn down a request. We have to meet the peak SLA. So we have the rest of the 21 hours of the day where we have various levels of sponge capacity, and we put that to work. And the data is right there, compute is right there, software is right there, there is no network cost, disk is spinning, we go party on it. So an example could be, let's say, a new image recognition or an optical character detection system where we have launched a new algorithm. We can go and rerun the last 6 months worth of data and add value out of it. Or it could be, I got a new message or a new meeting from a guy, and the last message that I got from him was 2 years back, and if the system could go and find that and draw some new insights that we can now show to the user, that's huge, right? And so we think that at that price point, the value is like completely dwarfs the cost. And that's the big win. From a business point of view, we say, okay, how can the cold data be valuable to us? As opposed to the cost at that point, the absolute cost doesn't matter, right? So that's kind of what we like the most about the model, in that as a money-making business, profitable business, we love it. We love the fact that the system lets us go and add value over cold data and just not store it and keep it as a backup, right? That's it. Yeah. Yeah.
Hi, thanks for the great presentation. I have 2 questions. One is, how do you handle the resharding of the data? And second is, how do you handle the users which are actually frequently traveling? So their mailbox will be constantly shifting, right? Because you said you shard it based on certain kinds of mailboxes and where they're going to go. That's how the logic is for the sharding. So how do you handle the users that are actually traveling all the time?
Perfect, great question. So the question was, how do we handle resharding, and how do we handle people who are moving around? Actually, that's great. I didn't mention it because I was trying to keep it really, really short. So the sharding actually is handled automatically. As in, when new users onboard, each user gets a shard. When a new group is created, each group gets a shard. So we don't even have to worry about it. Just the dynamics of users and groups and what people are doing is controlling what the shards are, right? The cases you may be thinking about is hot versus cold, which is there is a guy who just gets 1 mail a month, and there is a guy who gets 1,000 mails a day, right? how do we balance that? Law of large numbers works in our favor. Each server is handling several thousand shards. So just pure random, which is all we do today, especially with consumer and businesses all together, means that we are good. We don't have to get any very clever. Just put it in there, and it works. The second question was, what happens when users move around? It's actually beautiful. The data gets placed in the best data center where the user is accessing from, and all the compute is right there. So it just works, and we do that all the time. So and often clients request us, right? When they hear about us opening a new data center, we get requests to say, no, can I go there? And our system also does it automatically. And the movement is really simple. And we have online downtime-free data migration of the shard. Of course, if that was a question, that is built in. So without any downtime, we can move a shard. And once it's ready, we'll close it and open it here. And so that way, it's very seamless, right? And the routing plane picks it up within seconds and starts routing the request to the new shard, the new location. Okay, yeah.
Thank you for your talk. Do you have use cases that span multiple users at a time, something like, say, chat? And I was wondering if you do, does the choice of partitioning by user make it more challenging to implement those use cases?
Right, great question. So the question was use cases where the transaction naturally spans lots of users or many groups, what happens? You're absolutely right. This model has challenges when that kind of transactions grows, where the fan out becomes very large. Simple level of fan out in terms of, say, you send a request, like I said, to send a message to 5 people, or to chat with 5 people, or 10 people. It's all right. The basic fan out that we do will work. But cases where when we get to, let's say, a public chat involving a presentation with thousands of users participating simultaneously becomes challenging. So to be clear, this is not a solution that works for all apps necessarily. So this is sharing. If we took advantage of our knowledge of our application domain very, very deeply and made some of these choices, and it may be applicable, some of these principles in other applications like that, but for sure, there is no one size fits all, right? That many things for this will not work.
Great, thank you.
Yeah.
So for data living with a user, let's say I email a 10 megabyte PDF to someone else who's also using Outlook.com.
Yeah.
Do you guys care about that duplication?
Yeah, so data duplication. Do we do data duplication? We do in Outlook.com. We do data duplication in Outlook.com, where we place the copy of your 10 meg inside the OneDrive, which you can think of as the service that we didn't talk about. That is the single instance service, where the other users silently get a link, right? Yeah, so we do that. But it turns out that it's not as beneficial as people might think it is. We have that feature, but if you look at the actual win we get from that kind of a single instancing, it's not a lot. Basic compression gets us far more wins than that, and the complexity of managing the ref counts and creating a tight coupling often is worse than just keeping 5 copies. Yeah, there's a question there.
So in a global system where your unique handle in the user is sharded in your design, how do you enforce the identity being the email address across the globe?
Sorry, was the question how do you enforce uniqueness?
So if your email address is a@b.com,
yeah.
How do you ensure that your shards don't have different people with a@b.com?
Oh, I see. So how do we control that the identity of the shard is unique? Okay, that's a directory question in terms of when you sign up. There is a process that you go through that determines that your ID is unique, right? So that's a directory question. That's not at this level.
Design doesn't need to solve it.
Yes. That's right. So that is a centralized system. Think of that as a classic central database where you look up, is it already taken? Yeah.
Question.
Yeah.
I can see the upside of running multiple services on the same machine. What are the downsides?
Okay, for that, you have to see me after the talk. I know that's coming. There are downsides, for sure, yeah.
How often do you release code, roll out code changes?
Sorry?
How often do you roll out, update your service?
How big is the service?
No, how often do you roll out changes to your service?
We try to do daily updates to the service daily. And we also have the weekly updates that are slightly bulkier. So we have 2 trains. what we call the fast train and the slow train.
So it seems to me that you are over-provisioning CPUs, right? Had you done the provisioning the usual way, you probably could have run the same service at the same QPS for fewer CPUs. So how?
Right. So great question. I think he's saying, hey, we are probably over-provisioning CPU. In fact, it's slightly worse than that. The trade-off is, in general, we have to, the ideally optimized system will run at the red zone of CPU. Let's say red zone is 80%. Red zone of IOPS, let's say that's 50 IOPS per second. And the red zone of RAM and the space on the disk. The problem is it's really hard to hit the red zone of all four simultaneously. And you're right that if you were to build them as four separate systems, the chances that you could run each one closer to its red zone is probably higher. Right? But in practice, we have not seen, I've seen lots of services in Microsoft and outside Microsoft, and nobody comes even close to any of that. Here, at any given point in time, we are slightly closer to the red, away from the red on one of the four dimensions, and it keeps moving around. But at any given time, if you were to look, we are not that far off on any of them. And the simplicity, we take it any day. Right? You're right. If you can put a lot of effort to really fine-tune each one, we could get more efficient.
No, I get that. So my question was that what have you observed in practice when you moved from, you said that in 2013, you had the older model, or 2012, whenever you had your last big outage.
Our overall utilization went up in this model compared to the previous model.
So that's what I wanted, some numbers, if you have them.
Yeah, I mean, our CPU, we attempt to run, we try to run around 60% during peak is our goal. Our failure model is we have copies in 4 data centers, and we are prepared to run with one of the 4 data centers going down entirely. So we expect a surge to go from 60% to 80, 85% when that happens. So we want to kind of run at that number. And right now, CPU is our bottleneck. We have I/O, and more RAM.
Thanks.
Cool, thanks guys.